Организаторы просят. Okay, first of all, I would like to thank organizers for inviting me. It's my great pleasure to be here. And I'm going to talk about electromagnetically induced transparency, which was observed in isotopically purified rare earth ion doped crystals. These results were obtained some time ago in different experimental groups. I will present them during my talk. And of course, now we switch to another task, but I think anyway, we will continue this study in the nearest future. And moreover, we have some still open questions related to explanation of our experimental results. So this is not this is a live story, actually. Okay. Let me switch. Не работает. Okay, thank you. So I will start by making some general remarks about optical quantum memory, crystals, EIT, and then I will explain why we are interested in isotopically purified materials. And in the main part of my talk, I will present experimental results related to EIT in two crystals. Matrix is yttrium lithium fluoride, doped by neodymium and erbium ions. We already discussed quantum memory in the previous session, so I just mentioned that this device is used for synchronization of random processes in various quantum networks, quantum information processing protocols. So these devices are very important part for both quantum communication and quantum computing. And one promising approach to the problem is to use atomic ensembles for storage. And advantage of this approach is the possibility of multi-mode storage, which involves different degrees of freedom, spatial, temporal, frequency degrees of freedom. For example, we can store information about orbital angular momentum of single photons, etc., which is important resource for quantum communication, for multiplexing. And of course, rare earth ion doped crystals are among the most discussed systems suitable for memory implementation because of long coherence times. And typically, at low temperatures, liquid helium temperatures, coherence time and storage time is limited by spin-spin interactions of impurity ions between themselves and with spins of the host material. And standard recipes to achieve long storage times are application of high magnetic field and or cooling down to low temperatures, use of materials with low concentrations of impurity ions, use of so-called magnetically quiet hosts with low nuclear spin density, such as YSO crystal mentioned in the previous talks, and use of so-called full clock or zero first order Zeeman transitions. And we will see that the last possibility will be important in observation of EIT in some materials. For example, in doing so, significant progress has been achieved, which already mentioned. For example, YSO crystal doped by europium ions. In this case, spin coherence time was observed about 6 hours. And exactly in this case, Zipf's transition between hyperfine sublevels of the ground electron states was used. In this case, the first derivative of transition frequency as a function of magnetic field proves to be 0 for all orientations of magnetic field. And as a result, we have smallest sensitivity of impurity ions to magnetic field fluctuations in the host material and long coherence time. So why we interested in isotopically purified materials? In order to explain in order to answer this question, we have to turn to another important parameter, namely inhomogeneous broadening of optical transitions, which in crystals doped by rare earth ions is typically of the order of 1 to 10 gigahertz. So we have a larger ratio between inhomogeneous and homogeneous broadening, and this is this is an advantage, of course, because we have high time bandwidth product for quantum memory based on photon echo, for example. On the other hand, some promising protocols of quantum memory based on gradient echo memory protocol, atomic frequency, require preparing of very narrow absorption peaks in such a inhomogeneously broadened profile, which is not a trivial experimental task. And on the other hand, some protocols, for example, based on off-resonant Raman interaction, are not feasible in such materials when we have weak optical transitions and strong inhomogeneous broadening. So we consider another possibility. Some crystals, when they are isotopically purified, demonstrate extremely narrow absorption lines. And in this slide, you see two exciting examples. The first one is ILF crystal, a well-known laser material. When only lithium-7 isotope is present in the matrix, then inhomogeneous broadening of optical transitions reduced from several hundred megahertz to about 10 megahertz. And you see a famous example in this review paper published in 2011, demonstrating 16 megahertz line widths with erbium ions. And we will see that even smaller values are achievable in these crystals. Another example which corresponds to high concentration of optical centers is europium chloride hexahydride. This is a stoichiometric material. And again, in this opposite concentration case, we have inhomogeneous broadening about 25 megahertz. So anyway, it is possible to use materials with a small value of absorption bandwidth. There are two benefits from this fact. First, isotopes in her papers some time ago. This is very interesting spectroscopic possibility. Not this slide. Yes. And the second advantage is that we can develop, or I can say that quantum memory scheme based on off-resonant Raman interaction become feasible in this case. Indeed, basic interaction scheme is shown here. So since the coupling constant between single photon field is inversely proportional to the single photon detuned delta here. So when inhomogeneous broadening is small, we can use small delta and we can use small values of control field power. And as a result, we can implement these schemes in materials with weak optical transitions. And some of them were developed in the group by Sergei Moiseev, in our group, and we hope that we implement these protocols in the future. However, at the moment, we try to implement electromagnetically induced transparency, which may be considered as an important step towards the realization of these schemes. On one hand, on another hand, EIT also used as an effect for quantum memory itself. So we can store and recall pulses using just EIT effect. So in this case, under application of strong control field, we can observe transparency window within absorption profile for the signal field, weak signal or prop field. And simultaneously, we have a strong dispersion, which provides, which results in slow light effect. Slow light propagation of the signal field. And of course, this effect has been studied in many papers in solid state materials. uh, most of them were carried out in crystals doped by non-Kramers ions, as shown here, praseodymium, for example, the European. And when we consider the Kramers ions, we can mention only 3 experiments in this case, and 2 of them were made in our papers, and I would like to present results related to this experiment. Why we are interested in Kramer science? First of all, because they have transitions in transparency corresponding to communication, optical communication lines, for example, erbium ion. And on the other hand, they have larger hyperfine splitting in the ground state, which allows us to store and recall broadband pulses. Also very important. Okay, so let me present basic results. The first group of results are related to ILF crystal doped by neodymium ions. These crystals were grown in Kazan Federal University, in the group by Stella Karableva. And EIT experiments were performed in Institute of Applied Physics in the group by Renat Akhmedjanov. In the experiments, we used ILF crystal containing 99.7% of lithium-7 isotope, and concentration of 143 neodymium isotope was about 50 ppm. Under such conditions, we have inhomogeneous broadening initially at least about 70 megahertz. And you see that here in the left upper corner, you see absorption spectrum. You see that hyperfine structure can be easily resolved in this spectrum, so we can establish correspondence between absorption lines and transitions between various hyperfine sublevels of the ground and excited state. From these experimental measurements in possession of the effective spin Hamiltonian for the ground state, which is known from EPI measurements, we can, by fitting procedure, we can obtain parameters for effective spin Hamiltonian in the excited state. This is important because it allows us to calculate dipole moments of all transitions, optical transitions, and identify lambda systems, lambda schemes, and found optimal conditions for observing EIT. In particular, when we apply longitudinal magnetic field, we can identify Zifos transitions between hyperfine sublevels of the ground state, and the most important one is observed about the field about 63 millitesla, shown here. In this case, we have the smallest curvature of the frequency as a function of fluctuations of the magnetic field. The smallest curvature potentially leads to the longest coherence time. This is the first transition. And what is also important, in this case, we have, we have two transitions with some sublevel of the excited state. And these transitions have equal dipole moments. So it's kind of symmetrical lambda scheme. And moreover, the upper level is radiatively coupled only to these two sublevels of the ground state. So this is a kind of isolated lambda structure, which is very convenient situation for observing Raman and EIT interaction and different Raman protocols. And actually, inhomogeneous broadening of these lines was about 34-35 megahertz. Basic experimental results are shown here. So, we observe EIT, and the transparency becomes larger near the Zifos transition, and shown here, transparency was about 30%. And what is more interesting is that instead of usual Lorentzian or Gaussian EIT window profile, near this Zifos point, we observe modulation structure of this transparency window. You see that this modulation structure disappears when we tune from this Zifos point. And we believe that this structure is related to super hyperfine interaction between neodymium ions and fluorine ions. So you see a picture illustrating how neodymium ions is surrounded by nearest fluorine ions. Why we believe in that? Because if we take parameters from Hamilton, super hyperfine Hamiltonians involving dipole-dipole interaction and covalent bonding, which were derived previously in a series of papers and explaining experimental results, EPR measurements, without any additional adjusting fitting of these parameters. We already have excellent agreement between theory and experiment when we calculate this modulation structure. So it's very, very exciting. And moreover, actually, this picture is actually a superposition of about 50 transitions between super hyperfine sublevels of two hyperfine sublevels. And this structure is rather sensitive to parameters of Hamiltonian, but without any additional adjustment, we already have a good agreement. However, it's difficult to explain how in this situation corresponds to Zipf's transition, not high magnetic field used in EPR measurements. So how to explain existence of super hyperfine splitting when G factors of two fine levels are equal to 0? So we're still working on it, and we try to finish and publish these results in the nearest future. And the second group of results are related to crystals doped by erbium ions. Again, these crystals were grown in Kazan by Stella Karableva group, but experiments were carried out in Germany, in the group by Pavel Bushov. At that time, it was a group in Saarland University till the end of 2019. Now all of them in different places, but anyway, we hope to, maybe in some future, we will continue our collaboration. So the aim of these experiments was to study these materials at ultra low temperatures. Why? Well, because erbium is a Kramer's ion, we can expect that long coherence time is observed under application of high magnetic field. However, at high magnetic field, there are no Zipf's transitions in this material, and therefore another possibility is we can use another possibility. We can apply cool down these crystals down to low temperatures instead of application of high magnetic field, and found Zipf's transition and maybe observe also long coherence time. And we exactly studied this possibility in this research. So we started with a crystal doped by even erbium isotope 166. Other parameters are similar to the previous crystals with neodymium ions. Basic experimental results are shown here. I just mentioned some points. So we observe in homogeneous broadening of optical transitions about 60 megahertz, which are similar to those shown in the review paper in 2011, but with another concentration a little bit of this purity ions. We identified optical clock transition at some value of magnetic field. It's not a full clock transition, it's not a Zipf's transition, but anyway, at this point, we observe increase of coherence time for optical transition. And the main result is shown here. We observed that for this optical clock transition, optical coherence time increases from several microseconds at liquid helium temperature to 300 microseconds at temperature when crystal is cooled below 200 millikelvin. So significant increase of coherence time when we reach low temperatures and when we use optical clock transitions. And for smaller concentrations of impurity ions, we observed even small in homogeneous broadening as 13 megahertz, which to our knowledge is narrowest optical transitions observed with erbium ions in solis. Okay, let me skip this. And again, next we turn to 167 erbium isotope with a hyperfine structure, and repeat the same steps. From experimental data we calculated, we obtained parameters for effective spin Hamiltonian for the excited state, and identify lambda structures, Zipf's hyperfine transitions, etc. One of them is shown here. And, exactly for this value of magnetic field, we observe EIT. It's important to note that we did not observe EIT for other points. So we observe it only at Zipf's point, only at Zipf's transition. And moreover, we observe EIT effect only for temperatures below than 1 Kelvin. Eventually, when crystal was cooled significantly below 1 Kelvin, we observed transparency about 60% in this material. And this for this first observation of this effect in this crystal topped by erbium ions. And without going into details, I just would mention that we have a good agreement between theoretical simulation and experimental results, describing dependencies on magnetic field, temperature, for example, describing dependence of delay time in the EIT regime on the magnetic field and on the temperature. And you can find these details in our papers, of course. Well, let me come to a conclusion. I think the main results are, first, we grown and study isotopically purified materials. Some of them were studied at ultra-low temperatures for the first time, and this is very interesting direction of research. I think because it's important, for example, for developing quantum interfaces between microwave and optical transitions. And now you can find some papers devoted to studying crystals doped by rare earth ions at temperatures below 1 Kelvin. For example, recently a paper published devoted to YSO crystal doped by some ions, I don't remember, maybe erbium, cooled down to 100 millikelvin also. And they observed increasing of coherence time also. And finally, we believe that we, for the first time, observed super hyperfine structure of energy levels via EIT, via optical spectroscopy in EIT regime. This is also interesting result and may open the possibility to engineering some maybe super hyperfine transitions via Raman optical excitation. That's all. Thank you. Thank you for your attention.
Alex, have you any questions? Just maybe I can ask. Alexey Alexeyevich, please explain. You have the force transition, but you have lambda scheme, and the force transition only for one transition. Yes, only for one of them.
Only for one lambda? You mean only for one lambda scheme?
Лямбда схемы только на одном переходе the force, да? На одном, там, где сигнальное поле подается. На обоих. Вот это вот the force, да.
The force transition corresponds to hyperfine sublevels, right?
Okay. EIT, когда смотрите, там же два перехода, да?
Да.
Один переход и второй. Да. Это вот на одном переходе, где сигнальное поле, the force, что ли, да? А вторая.
These two, эти два подуровня как раз и соответствуют лямбда-схеме.
То есть
на каждом
переходе.
Да. Тут возникает, во-первых, зифос в отношении частоты самого перехода. Ну и вы видите, что как бы производная для каждого уровня, она тоже обращается в ноль. То есть не только разность частот, но и частота каждого уровня, ну как бы каждый уровень, он тоже как бы имеет нулевую производную. Поэтому здесь они совпадают, да. И в результате у вас получается симметричная лямбда-схема, когда дипольные моменты одинаковые. Да. Ну, зифос это же имеет отношение прежде всего к переходу. Вот 1-2. То есть У нас трехуровневая схема, уровни, сейчас, может быть, я перейду на другую картинку лучше. Ну вот, да, вот здесь, вот, да. Вот, один, ну ладно.
И на каждом переходе, вот на омега-1 и на омега-2, везде у нас Z-force.
Нет, на оптических переходах этого нет, потому что производная на оптической частоте, она не обращается в ноль. А на сверхтонком переходе производная обращается в ноль. Поэтому вот полный часовой переход мы имеем вот здесь, как стрелка показана, синяя. На микроволновом переходе. На оптическом переходе при этом магнитном поле часового перехода нет. Да. Это да.
И второй вопрос. Какая длительность была в медленном свете, когда вы использовали медленный свет?
Там десятки наносекунд.
То есть довольно короткий, да?
Ну, да, несколько десятков наносекунд, скажем так.
То есть и ширина соответствующего вот этого провальчика тоже, да, порядка?
Ну, там вообще разные режимы. Я, наверное, даже, может быть, поторопился, скорее всего, даже подлиннее, да, потому что ширина окна, она порядка там, сейчас я вспомню, 15 мегагерц. Но, в принципе, это позволяет там порядка 100 наносекунд, да. Я думаю, что вот так.
Но память пока не делалась.
Нет, память не делалась.
Все.
Yes, may I ask a question?
Да, Марина Николаевна.
You have shown a beautiful picture of super hyperfine structure, but it is, yes, really. But the super hyperfine interaction.
Не слышно, Марина Николаевна. Не слышно.
Oh, do you hear me? These super hyperfine interactions are not favorable for the coherence of the ground within the hyperfine levels of the ground state. So, do you suppose to overcome this difficulty?
We do not consider this as a favorable situation. We just see this experimental result, and
Yes.
it was unusual for us. But you can see on the right picture that the line width of each peak actually increases when we tune from the Z-force point. So it disappears, and we have the longest coherence time at Z-force point, and exactly under this condition, we can observe this structure. Otherwise, it cannot be seen. Therefore, we made conclusion that at least at this point we have the longest coherence time at this value of magnetic field, and we can resolve super hyperfine structure. Of course, maybe it's not favorable from other point of view, but it justifies that Z-force is helpful approach to achieve longest coherence time.
You're right. Thank you.
Thank you.
Есть еще вопросы? Ну вот все-таки как быстро уширяется линия вот у вас, когда от 60-58 миллитесла и 58, да, всего лишь чуть-чуть, и уже такое уширение, да? Правильно?
Ну, в общем, да, там чем дальше, тем быстрее. То есть, собственно, да. То есть здесь некая плата, ну, даже ближе, да. А дальше уже, чем дальше, так сказать, отстраиваешь, тем быстрее происходит уширение.
Давайте еще раз благодарим за очень интересный доклад.
Да, спасибо. Thank you.